So, so let's go on to this next bit. So imagine now we have a family of charges, and I want to know what's going on at this particular point in terms of, say, its potential. So is potential a vector or a scalar? It's a energy per coulomb. Is energy a vector or scalar? Do you have 8 joules in that direction? Isn't energy like mass? Yeah. So, yeah. So energy is not a vector. Energy, coulomb's not a vector. Divide one scalar by another scalar, you don't get a vector. So potential is a scalar, just like potential energy is a scalar. You can have a potential difference. That has a direction. That's a vector. Just like a temperature difference is a vector, but temperature is not. So this is a scalar, so we don't have to worry about the direction of things. We just have to work out what's the magnitude of the potential caused by this guy, what's the magnitude of the potential caused by that guy, what's the magnitude of the potential caused by that guy. And so it's just the basic equation. If V is equal to KEQ over R, and you got more than one Q, just add them all up. Now, each Q has a different R, so we can't just add the Q's together and use the same R. So it's KEQ over R for each individual one. So it's pretty simple. Okay. Now, if I know that I have the potential energy now, imagine bringing these two charges near each other. So now I've got to take into account this guy. There's a potential here caused by that guy. And then I have to bring in this Q2. So I'm going to say it's Q2 times the potential caused by Q1. Well, the potential caused by Q1 is KEQ1 over R. So then I say, well, it's Q2 times V, which is Q2 times KEQ1 over R, which is KEQ1 Q2 over R. So it makes sense. It's like you can derive that pretty simple. You can learn it if you want. If you want, you can have, you know, these two guys affecting each other, and those two guys affecting each other, and those two guys affecting each other. So we have 3 potential energy terms. So we have the first term, the second term, and the third term. And the first term is Q1 and Q2, those two, divided by R12. Q1, Q3 divided by R13. Q2, Q3 divided by R23. It kind of makes sense, doesn't it? It's not a big deal. This is an important bit, and frankly, I don't think I explain it that well. But basically what we say is that change in potential is equal to minus the integral of E dot ds. E's constant, so we're not talking about that one there, we're talking about this one down here. E's constant, so we take it outside. So it's E dotted with the integral of ds, which is S vector. So there's our electric field, and then there's our S vector. So we're back on that, yeah? And then we say, oh, therefore my little bit of potential is equal to minus E times my dotted with my little bit of distance. So there's my ds. So my little bit of potential, dV, is equal to my little, you know, etc. Yeah, you got it? Shouldn't be drawing it as a vector. It's my little bit of potential caused by that guy. Okay. If the electric field has only one component, say in the x direction, then we say E dot ds is equal to the magnitude of E in the x direction multiplied by the little bit of distance in the x direction. So the little bit of potential is equal to minus E dot ds, which equals minus Ex dx. And then you rearrange. So you get Ex, my electric field in the x direction, is equal to minus dV by dx. And what is V measured in? And what is X measured in? So that's where you get your second set of units for. Yeah, electric field is in newtons per coulomb, but it is also in volts per meter. This tends to come at the very end, this, I would say E is equal to minus dV over delta X. I prefer that form. And people forget it. So it's the voltage divided by the separation. It's the steepness of the embankment. Yeah, that's the visualization for it. So don't forget that one. Let's do one. Let's reinforce it. Have I got time? Yeah, let's do one. So let's do this. Let's go here. A pair of parallel plates are 3 meters apart. A 6-volt potential difference is connected across them. This is why a diagram's worth 1,000 words. What is the electric field in the gap? So I got a metal plate, I connect a 6-volt battery across them, 3 meters between them. What's the electric field? So you say E is equal to minus dV by dt, dx, which equals minus 6 over 3, which is minus 2 volts per meter, which is also equal to minus 2 joules per coulomb. It's the same thing. I'm a little bit uncomfortable with this negative sign. So that's the positive, and that's the negative. And what that negative sign means is that my electric field, I think, is pointing in that direction, E. Yeah, I get it more from my diagram than the sign on this thing. So I'm a little bit uncomfortable about that. I'm going to do a bit of thinking about that. I get it more from my diagram. There's the top electrode. There's the bottom electrode. There's my potential difference, delta V. There's my delta X. And there's the slope of my embankment. Yeah? Does that visually make sense? Yeah. Yeah. So
the electric field will always flow from positive to negative.
Oh yeah, always, yeah. The last little bit. All right, so we have this cloud of charge, and I want to find out the potential at this point caused by. I want to find out the potential at this point caused by this charge. So I divide by I'll do this again. There. So I'll divide this up into a whole bunch of cubes. And each one of them has a certain distance, so each one of them gives me a value. I don't need to worry about the directions because it's a scalar. And I say, well, for each one, my little bit of potential is equal to KE times a little bit of charge over the distance to that little bit of charge. And as I go to the limit, my summation, which I had before, becomes an integral. Yeah, that sounds awful. There are 3 possibilities. Pardon? That's going to be an issue, isn't it? So, there are 3 possibilities. I only care about this one. It's not that these are not doable, they're long. They're long. And it's more, it's like we always take the highest symmetry in physics. Think about this. I want to really emphasize this because this is a case where it looks horrendous, but Think about it. V is equal to KEQ over R. Agreed? Look at the point of interest. It is on the axis. So R is the same for any one of these dq's. So if I say V is equal to the integral of KEQ dq over R, I simply say, oh, R's a constant, which equals 1 over R times the integral of dq, or KE, times over R times dq. What is the integral of dq? Oh, KE over R big Q. I don't want my answer in terms of R. Nice right triangle. Oh, this equals KEQ over the square root of A squared plus B squared. Pythagoras. So after a while, frankly, when you start seeing this stuff in the book, I know it's Pythagoras. I know you're getting there by Pythagoras because you see that form over and over again. So that's familiarity with that's time on task. Just recognizing it. So I used to ask people to do this differentiation, this integration, and I stopped because it was like pretty pointless. That is a fair game equation, and if you have to learn that as opposed to that, then I think you need to just step back a little bit, because it's obvious that if you know this one and you know Pythagoras, you can get that one. Isn't that true? It's visualize. Don't rely on equations instead of visualizing. Last little bit. Let's imagine that there is a conductor. Charges reside on the outside of the conductor. They put them in a skin around the outside. We know from previous stuff that the electric field inside that conductor is 0 because we did it, yeah? We did Gauss's law. 0. And then we had inverse square law on the outside. What we've learned now is that on the outside, the electric potential is going to be an inverse relationship. And what I've not proven to you, and I just don't have time, I'm not going to prove it to you, I'm already a chapter behind, is that that's a nice constant value inside. Okay? So just a thing to end it up with. And we'll call it a day there.